Welcome everybody to today's session of the IAMP Math Physics Seminar. As most of you know, the seminar is organized by the International Association of Mathematical Physics and takes place online approximately every 2 weeks. All the talks are recorded and the videos are available online. If you're interested in other activities organized by the association, you are very welcome to check out the webpage. Okay, so back to our seminar. Today we are very happy to have here Jeff Schenker from the Michigan State University, who is going to tell us something about finitely correlated states for disordered systems. Thank you, Jeff.
All right. Well, thank you to Margarita. Thank you to all the organizers. I'm very happy to speak. I've enjoyed a number of these seminars over the last few years. Can't always attend because of other conflicts, but it's always fun when I can. Okay, so I'm going to tell you a few things about projects I've been working on with my postdoc who's currently working with me, Eric Roon, and then 2 graduate students are involved in some of the work, Owen Ekblad and Eloy Moreno-Nadales. Should give a plug for Owen that he's graduating this year and is on the market. So you may see a postdoc application from him. And okay, so first I should tell you something about what. Okay, there we go. What finitely correlated states of quantum spin chains are. So first of all, and because I was told to start basic, although I'm quickly going to get not terribly basic, I should explain what do I mean by a quantum spin chain. And I'm going to be a little bit vague on a few things here. So we have a one-dimensional system of quantum spins aligned in a chain. So this is a many-body system as opposed to single particle model. So we have more of a statistical mechanical model, although we're going to be concerned with things like ground state properties here. So the spins are indexed by the integers. So we have just a chain of spins. And each spin has an observable algebra. So, I mean, people typically use the word spin, but there's not always really sort of physical spin sitting around here. But if you want to make the connection, the dimension of the matrices you would use would be 2s plus 1 if you have a spin s at each site j. And so at each site j, we have this observable algebra, which is just the set of d by d matrices. And if we take some finite collection of these spins, then we know what the observable algebra should be. It's the tensor product of them. And then there's a standard construction on how you produce the observable algebra for the infinite chain. Essentially, it's everything that can be approximated in norm by finite volume operators. If you want to get sort of fancy mathematical terminology, it's the norm closure of the direct limit of the finite volume algebras. But basically, you have the finite volume algebras. They can all be, you can think of them as contained in one another in a very natural way. So if I have a smaller volume, I can tensor with the identity on all the sites outside the volume and include the operators in the small volume. And since these are all contained in each other, we can take the union. It's a normed space. We take its closure, and this is the observable algebra on the full chain. Okay, so that's a quantum spin chain, or at least part of it. I guess if you're really technical here, I really haven't done anything one-dimensional yet because I've just taken finite sets, but that will come in at the level of how interactions are formulated. So what is a state? Well, a state in quantum mechanics is in a finite dimensional setting is a density matrix. But what is that? One can also think of it as a positive normalized linear functional on the observable algebra. So in other words, we have a linear map from the algebra of all the observables to the complex numbers with the property that if I take a positive element, I get a positive result. And if I take the identity, this is the normalized statement, then I get 1. So this is a generalization of the idea of a probability measure, or if you like, the generalization of taking the trace against a density matrix in a finite volume setting, finite dimensional setting. And the idea is that if we have an observable and our system is in state nu, and we measure the observable, we should have the expected value for that measurement of nu of a, which is the expectation of the observable in this linear functional. Okay, I'm not going to get into any more details about that. It's just important to set the background as to what a state on the algebra is. So let me now introduce the notion, which when you see it this way may seem a little bit funny if you haven't ever seen it before. So I want to talk about this notion of what a finitely correlated state is. And this terminology, finitely correlated state, is due to the paper of Nachtergaele, and Werner from 1992, in which they were working to understand the general class of states that were like the solution to the ground state to the AKLT model that had been introduced a few years before. And they give a more general notion of what a finitely correlated state is. I'm going to focus here for simplicity on the idea of a purely generated finitely correlated state. So we have a state on the algebra, but it has a very special structure in the sense that we have a transfer operator. So there's a missing composition there. We have a transfer operator, which is denoted by E in this formula. So if I take observables at the sites in an interval, I can consider the tensor product of all of those observables. This is an element of the algebra of observables on the full chain. And I can look at the expectation. And the finitely correlated state is one in which when I take that expectation, there's a simple way to compute it using this transfer operator. So the transfer operator takes an element of the single site observable, a single site algebra, and it returns it also takes as input so that's this subscript A here. It takes as input another matrix B, which is an R by R matrix where a system has size D, had the dimension of the observable A is D by D. And what do we do with it? Well, we tensor A with this auxiliary matrix B, and then we conjugate with a partial isometry that pulls us back down to D dimensions. So when I take A here, I take the tensor product with B, I end up with a dr by dr dimensional matrix, but I'm going to hit it on either side by this matrix V, which is an R by dr partial isometry. So V dagger is the identity. And that pulls me back down so that this is now an R by R. Oh, apologies, I said D by D, but it's pulling me back down to R by R. So now you might say, what is R? What does it have to do with anything? It's an auxiliary thing called the bond dimension of the state nu. There is a way of thinking of this as sort of a projection of a product state. This is this valence bond picture. But I'm not going to get into that. Whereas you take a product state on a larger system and truncate it down to the spin chain. So the key thing here is that we are able to express expectations like this, which is there are a very large number of observables that one could write down here, right? If I have a D-dimensional spin system, then each observable has D squared sort of variables sitting in it. So there are, exponentially many variables in D squared sitting in here, whereas the formula over here actually has a very small number of parameters in it because I just have to specify essentially this matrix V. So this is a massive compression of the information required to describe the state, which is why they're they've been so useful both for the theory of some systems, but then also play a role in the density matrix renormalization group, because obviously you can store the specification of this transfer map much more easily than you can store the full state. So you can do computations with larger systems that way. Okay, so if you've not seen these finitely correlated states or matrix product states, which are their finite volume version before, this is probably going to seem kind of impressionistic. The main thing you want to understand is that there's this sort of transfer matrix formalism using a finite dimensional auxiliary space for computing expectations in a finitely correlated state. Now, you might say, okay, that's interesting, but are such states useful? Do they actually show up? So here is a theorem that summarizes parts of the paper of Nachtergaele and Werner, the ones that are sort of important for the discussion here. So the actual result stated here doesn't appear in the F&W paper. It's in a bunch of different results, and I've just grabbed things together. So the first thing that is this statement that the set of finitely correlated states, as I just defined them, is actually weak star dense in the set of all translation invariant states on the algebra. So, and this is in some sense the basis of what I just mentioned, the density matrix renormalization group. If I want to approximate a state, I can use finitely correlated states to do so. I'm allowed to do that theoretically. There's a bit more physics in it too. It has to do with the fact that the ground states of local Hamiltonians typically are well approximated by matrix product states, at least in the situations where the DMRT works. That was kind of tautological. So now I referred to so there's F&W give a slightly broader notion of finitely correlated states. I'm going to go back to the previous slide, sorry, in which they don't require this particular form for the transfer operator. There's essentially they require something that could be a convex combination of things that look like this. And they call this a purely generated finitely correlated state. And it turns out that purely generated finitely correlated states are in fact pure states. So the notion of being a pure state would be being an extreme element of the set of states on the algebra. The other thing that is really key here is that if I have a purely generated finitely correlated state, and I have the transfer operator, such as I defined it on the previous slide, and I look at the transfer operator associated with the identity. Sorry, I'm going to go back to the previous slide. I keep apologizing because I was just telling someone else last week to avoid designing their talk based in such a way that they have to go back and forth between slides. So I'm not following my own advice. Right. So what happens, so the transfer matrix of the identity is sort of relevant to this composition here, because if we we can always there's not a unique way to represent the observable, even if it's just a product observable as a tensor product of elements. I could always pad it by extra identity operators on either end. Or if I want to compute the correlation between two observables that live at site M and at site N with nothing in between, then there's going to be a long string of identity operators in the middle here. And so, you can think that expectations like this are going to typically involve large numbers of products of the transfer operator at the identity sitting in here. So the properties of that particular map have a great deal to do with the properties of the finitely correlated state. And in particular, if this map is eventually strictly positive, becomes strictly positive for some n, and I will define the notion of strictly positive later on, but you can simply think that what it means is that if you handed a density matrix, it returns a full rank density matrix. So no zero eigenvalues. So for large enough n, if that happens, then it turns out that the state, this finitely correlated state, has exponential clustering. In other words, we have exponential decay of correlations. And the state is the unique ground state of a gapped finite range translation invariant Hamiltonian. Of course, there's not a unique Hamiltonian. A given state can be the ground state of many Hamiltonians. But the point is that we can find one, and it's a local Hamiltonian. It's finite range even, and it has a gap. And this actually, of course, was the big interest in the AKLT model in the beginning, was as an example of something that that has a gap and was in the same hopefully in the same phase. I think that's understood now as the models considered by Haldane in his conjecture. Okay, so right, so this is the sort of general idea of finitely correlated states and the role that they played. I think it's time to give an example. And the example I'm going to give are what I call but these also appear in the F and W paper, are these generalized AKLT states. So we take our partial isometry to be this particular matrix. Oh, right, don't use the pen. This particular matrix, which if you want to use Pauli spin operators, maybe looks a little bit more understandable. So if I use the raising and lowering 2x2 Pauli spin operators, I can think of this matrix as 3 2x2 matrices in a row that have this particular form that I've written here. And so here we're looking at a three-dimensional site observable algebra. So in other words, it's a spin one system. And indeed, the AKLT model was formulated in terms of spin ones. And there's a bond dimension of 2. And indeed, actually, the original AKLT approach to it involved writing the spin ones as a combination of 2 spin 1/2. And so you can see where the bond dimension 2 is coming in there. So this map is easily seen to be a partial isometry. If I take V theta dagger, I get the identity, the 2x2 identity. Yep. And if I take theta that is between 0 and pi over 2, what's the relevance of 0 and pi over 2? Well, if I'm at theta equals 0, then of course sine theta is 0, and so this middle part drops out. If I'm at pi over 2, then the last two parts drop out, and so there's clearly something singular going on at those points. And I don't need to consider other thetas because I get some signs change, but I can sort of gauge my way back to theta in this range. So for theta in this range, the associated finitely correlated state that uses the transfer operator that you build out of this partial isometry, F and W show that this is the unique translation invariant ground state of a gapped nearest neighbor Hamiltonian. And in fact, so in this case, it's actually nearest neighbor. If you specialize to the value of theta that gives you cosine theta equal to the square root of 2 over 3, then the state you get here is the ground state of the AKLT Hamiltonian, which I've written down here in its sort of traditional form, and where the boldface SJ is this sort of the standard vector of spin one operators in the 3x3 matrices. Okay, so this is an example of a finitely correlated state. I want to show sort of a little bit of how do you actually use these things? How can you actually compute? Why are they so simple? And we're going to get to a formula that will be generalized later and be useful at the end of the talk. So we have this partial isometry. We produce this transfer operator using this conjugation after taking the tensor product. So here A again is a 3x3 matrix, B is a 2x2. A is an observable, B is an auxiliary matrix. And you can start doing some computation. So we can look at the transfer matrix at the identity. And remember, that plays an important role in the state. And you can quickly check. So this is this top line is just a formula that you can quickly check for how the transfer matrix at the identity, the form that it takes. And you can, so The transfer matrix of the identity is a linear operator on a space of dimension 4, the 2 by 2 matrices, right? So, and it turns out it's actually a symmetric operator in the usual Hilbert-Schmidt inner product. So, right, so it's self-adjoint. So it should have 4 eigenvectors with real eigenvalues, and indeed you can simply write them down. They are if you start guessing things, you would find them quickly. First of all, the identity is an eigenvector. You can check that if you plug the identity in here, the cosine squared plus sine squared come together, and you recover the identity. And the other eigenvectors are the Pauli spin operators. The sigma z spin matrix has this eigenvalue, cosine 2 theta, which comes from a cosine squared minus sine squared that you get here. And the raising and lowering operators, or indeed sigma x and sigma y, since they're linear combinations of the raising and lowering, are also eigenvectors with eigenvalue minus sine squared. And the key thing here is that if theta is between 0 and pi over 2, these two numbers are strictly less than 1, which means that, right, as I take high powers of this transfer operator, it's really just this part that will dominate, and that's where the eventual strict positivity comes from. And then you can check what happens with some other operators. So if you look at the spin z operator, observable, you look at its transfer matrix. Well, spin z, right, has a 1, 0, and a -1 down the diagonal. The 0 hits this piece, kills it off, and the 1 and the -1 come together with the 2 pieces at the ends, and you get an expression that looks like this with a minus sign in the middle, and a cosine squared. And again, I'm not going to write down eigenvectors and eigenvalues now. I'm writing down something that's useful for the computation that we're doing. If I plug in the identity, I get something a multiple of the sigma z. If I plug in sigma z, I go back to the identity with an overall factor of cosine squared or minus cosine squared. Okay, so why did I write that down? Well, here's an exercise. You can compute a correlation in this state. So if I take the spin z matrix at site M, and I take the spin z matrix at site N. So what you want to think about is that this is sort of SMZ, tensor the identity, all the way up until n-1, and then you get SNZ. And if you just use the transfer matrix formalism, you discover this formula for the correlation, which you can see indeed decays exponentially. I mean, it's important if you first compute the one point thing, take the expectation of the SZ matrix, you'll discover that it is 0. The model actually has a symmetry with respect to spin flips, so that isn't surprising. But it's important here because if I'm talking about decay of correlations, it should be a truncated correlation, right? And so it's important that the observables I'm taking the product of have mean 0. Okay, so we have an explicit formula, and as long as theta stays away from 0 or 2 over pi, this thing decays exponentially. You might say, well, if theta's pi over, well, actually no, pi, sorry, yeah, 0 or pi over 2, right? It decays exponentially. If I go to pi over 2, well, it happens to be 0 because of these cosine theta terms out front, but there would be other observables that don't decay. Okay, so that's just to give you something to hold on to, and we're going to come back to this calculation in a slightly different context in a bit. Okay, so now I want to talk a bit about non-translation invariant finitely correlated states. And in the most general sense, you can actually define a very general sort of finitely correlated state. Again, I'm going to talk about this sort of purely generated formalism. You could generalize it a little bit more by taking various convex combinations of things. But suppose you have just an arbitrary collection of partial isometries that go from d by dr partial isometries, and I'm going to use at the site J, I'm going to use the transfer matrix associated with the corresponding partial isometry. In other words, I'm going to I'm going to, when I want to take the expectation of a product observable, I'm going to use a different transfer matrix for each factor here. And the key thing that I would need, instead of, previously I needed this density matrix, this R by R density matrix that was preserved by the transfer at the identity. Now what I need is a sequence of density matrices that is mapped one into the other by the transfer operators. And so if you give me the data 1 and 2, I can simply define a state. And this is a sort of non-translation invariant generalization of what a finitely correlated state is. By the way, if there are any questions, please feel free to interrupt me. I would, yeah. Okay. So for instance, we can define a sort of generalized non-translation invariant AKLT state. You give me an arbitrary sequence of angles, theta j, and I can simply define a state that that looks somewhat like the AKLT state, but just simply involves different angles at every site. And you still have an exact formula for, say, this expectation of a product of spin z's. It's just, instead of a cosine of 2 theta to a power, now I get the product of the cosines at the different sites. Okay, so now, of course, that's extremely general. What I'm actually interested in is finitely correlated states for disordered systems. So suppose we have a disordered system with homogeneous disorder. So for instance, we could have a Hamiltonian, which is a disordered Hamiltonian, and but in such a way that it's translation invariant in distribution. So we want a system that's translation invariant in distribution. And then we might ask, what kind of state should we use as a finitely correlated state approximation of the ground state? Or maybe, can we write down frustration-free translation invariant in distribution systems with finitely correlated states as ground states? And here is the sort of general sort of thing that we would like to obtain. So let's suppose we have, so here I'm going to get into a little bit of sort of ergodic theory that comes up quite naturally in disordered systems. And I'll give some examples which are maybe more down to earth in a bit. Well, actually one example. So suppose we start with an ergodic dynamical system. So a probability space and a measurable invertible ergodic map. So remember, ergodic means that if that an invariant set under the map, so in other words, if T inverse of A is equal to A, then that set has either probability 0 or 1. And suppose we have a partial isometry valued random matrix. So in other words, I have a map from the R by dr matrices that is a partial isometry almost surely. Then we can simply define a homogeneous disordered finitely correlated state, or more properly, a purely generated one, by taking the sequence of matrices that I was discussing on the previous slide to be the evaluation of this random map along a trajectory of the ergodic map. Okay, and so for example, we can take this generalized AKLT where I take independent identically distributed angles. So I pick any distribution I like for the angle at a site. I take the product distribution for all the angles, and I can that model is of the form of this homogeneous disordered finitely correlated state. So we're interested in, what are the properties of such things? Can we do something like Finitely Nachtergaele Werner for such states? And this actually started a few years ago in a collaboration with Ramis Movasag, where we talked about something that we termed ergodic quantum processes, which I will now describe to you because I need a brief nugget of the result from that, and then we'll get back to the finitely correlated states. So, and for this, I need to introduce some proper terminology. So, oops, sorry. So we have, if we have a linear map from the matrices, from D by D matrices to themselves, the map will be called positive if it preserves positivity of a matrix. So if Z is a positive semi-definite matrix, then phi of Z is as well. It'll be strictly positive if whenever we give phi a non-zero positive semi-definite matrix Z, we get one that's actually positive definite, full rank. Okay. There's an associated notion that's important in sort of quantum information theory, which is that of a completely positive map, which has the property not only that it's positive, but it remains positive if you tensor with the identity map on an arbitrary additional finite dimensional algebra. Okay, and these are important in quantum theory because if your completely positive map is supposed to describe the evolution of a quantum system, then presumably it should remain positive even if your system is entangled with some auxiliary system, in which case that isn't changing at all, in which case this would describe the dynamics. And there are maps, the transpose map is an example, which are positive but not completely positive. So the transfer operator at the identity for a finitely correlated state is a completely positive map. So any map that can be written in the form that's indicated here is actually completely positive. It's called Steinspring's theorem. And the map also happens to be trace preserving. That's an important property that we need for finitely correlated states because we need to have a density matrix that is sorry, if we expand by products of the identity, we shouldn't change the trace that we're looking at in the end formula. So to get the expectation. So from the standpoint of finitely correlated states, one's interested in completely positive trace preserving maps or CPTP maps. Okay. So the idea of an ergodic quantum process is simply a CPTP map valued random variable. And so if we have such a thing, we have an ergodic dynamical system and we sample some CPTP map valued random variable along an ergodic trajectory of the ergodic map, we call this an ergodic quantum process. Where the name comes from, why it's a process, is that we think of these maps as describing the dynamics of the system over a discrete unit of time. And so if we want to describe the dynamics over a long time, we would compose many of them together. And indeed, this is sort of the motivation in the work that I will present briefly with Movesog, in which we're talking about sort of random open system evolution. So CPTP maps can also be used to describe the evolution of an open quantum system over a discrete unit of time. And so composing a number of them together like this is a picture of a general evolution of an open quantum system. But in our case, we're interested in in our case, in the finitely correlated state, we're not talking about dynamics, but we're talking about correlations along the chain. And we still are interested in compositions of them since we want to compose many factors of the identity transfer matrix of the identity. And so this is another ergodic quantum process. But the question that Movesog and I were asked is, what happens in general to the composition of these things? So it is at its heart a composition of random matrices. And so there are some general results that apply to that, Osciletic's theorem in particular. And the result that we obtained is a sort of adds a little bit of information to Osciletic's theorem in this context. So suppose we have an ergodic quantum process that is eventually strictly positive, and that should remind you of the condition that was needed in FNW to get exponential clustering and unique ground state, of a finite range Hamiltonian, which was when a single map composed together was eventually strictly positive. So by eventually strictly positive, we mean that if we compose our process together, it's with probability 1, we get strictly positive for sufficiently large n. So in other words, for each realization of the randomness, there is an n past which the map is strictly positive. Well, then we get a unique solution to this cocycle equation, which is, sorry, this should be a subscript n here, not a superscript n like that. So we have a density matrix for each at each time n, or at each site, which is pushed forward to the next site. And this density matrix is strictly positive almost surely. And furthermore, if I take the evolution over a long time, for any initial condition, it gets close to this density matrix at large times with an exponentially decaying, with a non-random exponentially decaying rate. Okay, but this, and I'll come back to this, the omega here, C omega, this is a random prefactor constant that will actually be important later. Okay, so this is essentially a refinement of Oscillatus theorem. The logarithm of this mu is the second Lyapunov exponent for this product of random matrices. And essentially what we're saying is that under this strict positivity condition, the subspace in Oscillatus theorem corresponding to the second Lyapunov exponent has codimension 1, and there's a distinguished vector which is this Zn that is in its complement, that is actually a strictly positive vector. Okay. My student Owen Ekblad, who I mentioned before is on the job market, has obtained some very nice generalizations of this for quantum processes that are not eventually strictly positive. And there's a whole sort of reducibility theory where we can take processes and break them down into their irreducible components. And when the irreducible component has the strict positivity property, then what's in the Movasag, my paper with Movasag, is recovered. Okay. So now let's go back to the finitely correlated states. How am I doing for time? Okay. So I'm going to make there's a small strengthening of assumptions here. I'm gonna move to a continuous setting, and so previously I was simply talking about ergodic probability spaces. It turned out that for the purposes of really describing what we're doing in my work with Roon, we needed some continuity, which I'm not going to be able to get into why. So we're going to assume that our probability space is actually a compact Hausdorff space. Our probability is actually a radon probability measure, so a regular Borel measure, and the map T is a homeomorphism. So it's a continuous with continuous inverse. Now, this actually isn't a very large restriction. Most interesting probability spaces fit into this context, and in fact, there are theorems that describe that precisely. But I'm not going to look at that. I'm just going to take this assumption. But for instance, if you take independent identically distributed random variables like the angles, that certainly fits into this framework. And we're going to look at states, random states that are continuous functions of the disorder, which is also actually something that one typically expects to have with the right notion of the continuity. So we'll take a continuous random state is just a weak star continuous map from my Hausdorff probability space into the set of states on A. Okay. Weak star continuous just means that when I take the expectation of an observable, that becomes a continuous function of omega. And we'll say the state is translation covariant, or in other words, translation invariant in distribution, if when I shift the disorder by the ergodic map, I could just as well shift the state by the translation of the spin chain. Okay. And again, if you think to the IID generalized AKLT state that I wrote down a few slides ago, that is a translation covariant and weak star continuous state. And then simply to distinguish what we're talking about in the random case from the non-random case where F and W use finite finitely correlated, we're gonna call a state small. We'll say that it has small correlations if a condition that's very similar to the F and W condition holds, which is a bit, well, it's a bit, I guess, complicated to describe, but essentially, if I take an observable on the left half of the spin chain and I plug it into my state and I tensor with something and I define a linear functional on the right half of the chain by tensoring with that observable that I had on the left half. And taking the expectation. Well, that always defines a linear functional on the right half chain. It turns out that the finitely correlated states defined by F and W are exactly those states such that the set of linear functionals that you can obtain in this way is actually a finite dimensional set. So a priori, this is huge, the number of linear functionals you could get this way, right? You get one for every element of the algebra of the left half chain, but they may all be many of them may be the same, and that's what happens in these finitely correlated states, is this actually reduces to a finite dimensional space. And so in our case, of course, there's not one such space, it's a random space, because for each realization of the disorder, we get a space. And so we need that not just to be finite dimensional, but finite dimensional almost surely, right? We need this to happen for every realization of the disorder. Okay, and we'll say that it has small correlations in that case. And one of the theorems that we have obtained is could be summarized is, in a sense, is that Nachtergaele Werner works for random states. So, and here is it in words. So if I take a translation covariant continuous random state, then it admits a translation covariant transfer matrix factorization. So this is like the F and W factorization, but a non-translation invariant one, where the transfer operators are themselves random objects, but translation covariant random objects. It admits this with a finite bond dimension if and only if we have small correlations, in the sense that these sets of linear functionals that I get on the right half chain are finite dimensional. Okay. And actually, just like F and W, we can show that that there's a general sort of transfer matrix formalism valid for any state, but with it's kind of a triviality that you can do this, but with an infinite dimensional transfer matrix. And again, we can prove weak star density of the set of translation covariant random states of these. Sorry, there's a missing translation covariant continuous random states with small correlations. Right, so if I take the continuous translation covariant continuous random states with small correlations, it's weak star dense in the set of all translation covariant random states. Okay, so we can use them to approximate general translation covariant random states. And so this describes work in progress, but it's near to completion. So again, we have this sort of ground state property. So if we have a homogeneous finitely correlated state with a transfer operator that was like defined above, so this purely generated idea, then if the ergodic quantum process is eventually strictly positive, i.e., it satisfies the assumption that is sitting in the theorem of Mindwood-Lovesog, then we can produce a finite range or a locally finite range Hamiltonian, which gives this state as its ground state. So I emphasize the word locally, and the point is that the actual Hamiltonian may not be possible to find a finite range Hamiltonian. And that has to do with the disorder. But if I look locally, then the spread of interaction operators that act at a particular site is necessarily finite. So if I look at the Hamiltonian locally, it's finite range. but there may be sites way off in the distance which need a very large range. And if for those who know something about the finitely correlated states, what happens is that the injectivity radius becomes random and it becomes a function, therefore, of the position along the chain in the state. And so you need, you may have a different injectivity radius at different points, and it could be unbounded from above as a random variable. And what happens is that the local range of the Hamiltonian at a given site is closely related to how large we have to take a composition like this to get it to be strictly positive. Notice we do not assert that the Hamiltonian is gapped, and it turns out that a surprise here is that there may not exist a gapped Hamiltonian with a ground state, even though we have this exponential decay. And that's the thing that I'm now going to describe. And this is something that Roon and I have already, written up in our first paper. So suppose we take an IID generalized AKLT model. So I have these partial isometries, and I have this formula for expectations. Well, then, as I wrote down before, we have this formula for the correlation of, say, two spin z's. The nice thing about this formula is it's a product of independent random variables. So we can answer any question we want to about it, right? And so in particular, what we can show is that if we have the random generalized AKLT state, then we have exponential clustering with a non-random rate of decay at infinity. We can construct a nearest neighbor Hamiltonian. So it turns out that here the injectivity radius is always 2, and we can get the Hamiltonian to actually be nearest neighbor. It's, as usual, just a projection onto a particular subspace of the tensor product of two nearest neighbor sites. Sum of such projections. It's frustration-free. However, if either 0 or pi over 2 is in the support of the distribution of theta j. So that just means that we can obtain values of theta j that are arbitrarily close to 0 or arbitrarily close to pi over 2. Not that we can actually obtain the value 0 or pi over 2, because we want to explicitly exclude those. We can just get close. Then it is not possible for nu to be the ground state of a gapped local Hamiltonian. So in other words, the Hamiltonian that we've constructed is not gapped. And furthermore, so I'm not going to get much chance to talk about this, but one of the things about the AKLT state is that you can prove that it exists in a phase that's separate from the product states it's a symmetry protected phase. And one way of looking at that is through this index that the very nice paper of Tasaki looks into, which is the expectation of a particular twist operator, which he refers to as the Afleck Lieb twist operator, which has this form. Okay, and it turns out that in the AKLT state you get an expectation value of -1 for this twist operator, and the fact that it's -1 and not 1 proves that shows that it's in a different phase. Technically, I should take the sign of it should just be the sign. This limit does not have to have magnitude 1, but in this particular case, it actually does. So the general definition of the index involves just taking the sign of that term. And so some comments on this. So, right. So if I take the absolute value of this correlation function, it has this formula. I can take the logarithm of it, and I can immediately see what the exponential decay rate. It's simply the average. Sorry, I've done this here under the assumption of uniform distribution, but so in general, this should be a pi over 2, a 2 over pi, and this is some measure here. But what happens is that if 0 is in the support of theta j, then there will be arbitrarily long intervals of thetas for which these cosines are as close to 1 as we like. So although we always have exponential decay if we go far enough apart, if we go some distant place on the line, we can find an interval of length 1,000,000 over which the cosines are, within 10 to the minus 11th of, okay, I need to be careful about numbers there because, anyway, are extremely close to 1. And so I don't see decay over that interval. Okay, and this means this actually can be used together with an exponential clustering theorem of Nachtergaele and Sims that shows that when you have a gap, you have a particularly strong form of exponential clustering, which doesn't allow for such large intervals of where you fail to see decay, to prove that we cannot have a gap here. So there can be no gap to local Hamiltonian that has this as a ground state. Now, so this brings me to the last thing, and I think I have time to sort of go through. These are from this point on. It's basically all questions. So the properties of the AKLT state suggest the following definition. So suppose we have a state on which we have a bound on truncated correlations. Okay, we can write correlations using a commutator that forces them to be truncated. And so the kind of bound we get in the AKLT state is the following. So suppose I have an observable that lives on the left half chain and an observable that lives on the right half chain. And I'm going to take their correlation, but I'm going to take it when I translate the observable on the right half chain far away, off toward infinity, right? So that's what's expressed here. Tau x is a translation of A plus. And the kind of bound we get is something that looks like this. Obviously, we need to have the norms of the operators on the right-hand side. There's a non-random exponential decay I have here of e to the minus mu x, and then there's a random prefactor that comes in here. And it's this random prefactor that sort of is accounting for the non-uniformity here. If this thing is unbounded from above as a random variable, then there will be sites out along the chain at which this is a very large number, which sets the scale, the distance that I have to go before I can really detect the exponential decay. And we'll call something that satisfies this bound quasi-gapped. And we'll say a Hamiltonian is quasi-gapped if its ground states have this property. So first of all, quasi-gapped is a special case of quasi-gapped. So if we have the ground state of a gapped local Hamiltonian, then the estimate I had on the previous slide holds with a non-random C omega, right? That's that you can, right? So you get this. There was a question. Do the chains live in different spaces? Not sure I understood the question. Oops.
When you say that you translate,
Yes.
right, you have two chains, right? But if you translate one onto the space of the other, like can you do that, or there has to be like you are limited by chirality of which direction you translate?
So I don't think we're not considering something where there's, I mean, you could consider generalizations where there's something like that, but we have a fixed chain here. There's not one. So we're just taking, we're working with the chain and the usual translation operator on the chain algebra that doesn't involve any chirality or it's just it. So I don't know if that made sense. We can come back to that.
Okay. All right.
Yeah. Okay. So if, on the other hand, we have to take an unbounded operator, an unbounded constant in this bound. In other words, if the random variable is infinity and we can't improve on that, has essential supreme infinity, then we get back into the situation where we cannot have the ground state of a gapped local Hamiltonian. And here is just the explanation that, right, if I translate A minus, see, I end up translating the constant along the trajectory. And so if this can take very large values, then I have places where I have to go a very large distance away from y before I can see the decay. So now quasi-gapped Hamiltonians seem to be the relevant class of interactions for disordered systems. They're the kind of thing that you're likely to get. So for instance, if we move to a different setting, which is Anderson localization in systems of quasi-free fermions. So I take a one-particle model with Anderson localization, and I take the quasi-free fermionic model over that. Then this actually is a quasi-gap under the same definitions I gave above. I mean, I didn't define them for a fermion algebra, but you can modify it quite reasonably to do that. And the mobility gap exactly gives you decay bounds of the form that I'm talking about. They're not the uniform decay you would get if you have a gap, but they're sort of like that. So a natural question is, do we have some sort of localization properties for the low energy excited states of a quasi-gapped Hamiltonian? And there are various levels that you could ask this question at. You could go all the way of asking for sort of Anderson localization, some kind of something consistent, that's similar to Anderson localization. But you could also just simply ask, there's sort of, it's clear in the AKL, this generalized AKLT model that the absence of a gap has to do with these rare regions where I have variables near their extreme values. So you would expect the low-lying eigenstates to somehow live in those rare regions, or mostly only see observables in those rare regions. And that would be a weaker form of localization. So that's a natural question. And then the other quite natural question is, if you look at one thing that people are interested in with these, frustration-free models and finitely correlated states is in this whole issue of classifying quantum phases. So in that case, what you want to do is consider, homotopies between different Hamiltonians. And typically what is done in the literature is you consider homotopies between gapped Hamiltonians that preserve the gap. But you can introduce a new idea here, which is homotopies of quasi-gapped Hamiltonians, which preserve the quasi-gap. And now what do I mean by preserve the quasi-gap? They should preserve the rate of decay at infinity, right? If I go back to the definition of a quasi-gap, so here, this mu, 1 over this mu is sort of the gap, or something proportional to 1 over mu, right? And so if we preserve the quasi-gap, then can we still do, does that change how we classify quantum phases? One would hope not. If the idea of the, and if you look at, what goes on, for instance, in the analysis of the quantum Hall effect, this is exactly right. You can define the quantum Hall index within a gap quite easily. It takes a little bit more work to do it if it falls in the mobility gap, but ultimately one can prove that the index is actually constant as a function of the Fermi energy as you move throughout a mobility gap. So you can move from a gap into a mobility gap, and so you have something like this for the quantum Hall effect. And it's quite natural to ask that same question here. So for instance, if we have two gapped Hamiltonians, and we float at one another by a homotopy that closes the gap but leaves open a quasi-gap, you can ask, are they in the same quantum phase? And it's not at all obvious that they are, but I sort of physically, I would expect them to be, because the disorder should be, otherwise there's something sort of unstable about this idea of classifying quantum phases. Okay, so, and similarly, right now we have this computation as the Tasaki index for our generalized AKLT state, but we don't quite know what it means because we don't have a gap, right? And so we happen to have a state that has this nice index, but it doesn't have a gap. And so we can't say, oh, well, it's in the same phase as these other things. And it's not in a phase with something which has a different value of the index, because one would need to know that the index can't change along a homotopy that preserves the quasi-gap. So these are some interesting sort of future ideas for looking at this. I think this is a fruitful area to look into. So I think I've gone past my time. Apologies. So I'll say thank you and stop here.
So thank you very much. If you'd like to ask questions, please unmute yourself. Or comments. So maybe I have a quick question. So when you don't have randomness, you have this example with the thetas. That you say for any choice of these thetas, you have a gapped Hamiltonian. And now when you add the random or not?
Oh yeah, if you have a constant theta, it's gapped.
Right.
Right. But the gap does depend upon theta.
Right.
Yeah.
And even if you have variable thetas, I mean, but I fixed them, they're not random. Because then you take the thetas IID, and then suddenly you show there is, depending on the support of these, of I guess the probability. So if the probability distribution approaches 0 or pi over 2, then you don't have a gap. But if you stay away from 0 and pi over 2, I guess you still have a gap.
Right. Yes. Yes. If the distribution, well, okay, I expect so. We haven't actually written the proof of that, but I expect that you do have a gap, and it should follow by methods that exist in the literature. But technically, that result has not been written down. So yes, but I do believe that if you stay away from 0 and pi over 2, that you will have a gap.
Okay.
Yes.
And this probably should not depend on, so we are saying there are IID random variables.
I'm not using, the only property I'm using of IID random variables is that you have long intervals over which you see extreme values. So, right, I don't expect this, for instance, to hold for quasi-periodic sequences, because you don't have long intervals over which you see things that are, over an entire interval close to the extreme value. But you could easily, you could also think about non-IID models where you have such. So I'm not really using the full strength of IID.
So if you choose a proper configurations of thetas, you can construct some.
In fact, if you could really formulate a non-random statement using what I've shown on what I have up right now. If you just give me a sequence and I specify certain properties of the sequence, right? Just give me any sequence of thetas, and all I need to know is that there are long intervals over which I get close to the extreme values. Then that state cannot be the ground state of a gapped Hamilton.
Okay.
Yeah.
Okay, thank you.
Hello, I have a question. Hi, Jeffrey.
Hi, Alessandro.
Hi. So, can you clarify if taking a quantum spin chain like the AKLT one or whatever, generalized Heisenberg chain with random coefficient or random field, you get a model satisfying your hypothesis?
Well, okay, so this is of course a tricky business in all of this, because the weirdness about all this finitely correlated state business is that you end up reversing the role of state in Hamiltonian. So if you write down a Hamiltonian, chances are it is not frustration free with a finitely correlated ground state. Right.
In fact, maybe the question is, can you exhibit some example of Hamiltonian with random coefficients?
Yes. So we had, right. So I'm not gonna put it down because it doesn't have a pretty expression. But But certainly for this random AKLT state, we can define a nearest neighbor random Hamiltonian. The terms of the Hamiltonian will consist of, right, for each pair of sites, you will have a projection that onto a particular subspace of the tensor product of the two Hilbert spaces at those sites. And these projections will sum up to give you a frustration-free Hamiltonian. And the projection will actually be then a random object with the translation covariant, just it'll be a random object, and the projections that appear at various positions will just be the sampling of the projection from the origin along a trajectory. So it will be exactly of the form that you like. It will not be, a random field model. It's not like I'm adding a random field times SZ, because that wouldn't necessarily be frustration free anymore. But it will be a translation invariant in distribution random Hamiltonian.
Thanks.
And you can exhibit lots of them. It's harder to exhibit one that looks nice. I mean, the AKLT state is kind of a model, is miraculous because not only does it have this property, but it also looks nice. It has this simple expression in terms of the spin watt operators. But actually, even when you go to the sort of generalized AKLT state where theta is not such that its cosine is the square root of 2/3, the Hamiltonian you get, even if it's translation invariant, does not look as nice as the AKLT Hamiltonian, unless I'm forgetting something. If someone can correct me if they know about that. But yeah, so definitely there are examples.
This is Tasaki from different account. My main account, something happened. So can I ask a question? So so of course I'm interested in this final discussion about classification of SPT phases. So is it correct that in this quasi-gap case, if you look at, I don't know how, but if you look somehow at finite, very long portion of your chain and change your state continuously, keeping this quasi-gapness, then within this finite chain, your system almost looks like gapped system. Is that correct?
That should be correct. And actually, that is a question that didn't make it onto the slide. So it's clear in this random AKLT state that if you look at the local Hamiltonians, that the quasi-gap is related to sort of rare events on which local Hamiltonians have a small gap. So the typical behavior is a gap, but then very rarely you can get a very small gap. Where how big the gap you could get will depend on the system size and stuff. So yes, you should be able to do some sort of probabilistic kind of analysis where you rule out the bad situation.
Okay.
But I don't know, right? It's, that is a question. Like if I just give you something that's quasi-gapped according to the definition that I formulated here, does it have that property that we can see the quasi-gap in the statistics of finite volume Hamiltonians? And in fact, if not, then maybe this isn't the right definition of quasi-gap, because I think the right definition probably involves something with those finite volume statistics. So yeah.
Okay. Can I ask a more technical question? So you define all these non-translation invariant finite correlated states by sort of purely generating this. And are these finitely correlated states pure also in non-translation invariant cases? Okay.
Yes, they are pure.
You can prove
I did. Yes, we can prove that. Yeah.
Okay, thank you.
Yeah, and in fact, the proof is very similar to what's in Nachtergaele.
Okay, that part you can do for non-translation invariant case.
Yeah. At least if they're random. I mean, I think if they're random. I mean, we actually haven't. I gave as an example this sort of very general thing where you just specify a sequence. We haven't done very much for that. We really are assuming translation covariant.
Okay. Right.
Then
you can
just
prove pure.
Then we can do it. Right. Yeah.
Okay. Thank you.
More questions? Comments? Complaints? Okay, no, doesn't seem so. Okay, so I think so we thank Jeff again, and we can close here the official part of the seminar.